This video is on Hashtable, its implementation, and the time complexity of its basic operation. Here's a roadmap of what we will cover. In this video, we will dive into one way to handle the collision issues in storing data into a hash table, which is called chaining. And we will use it to implement the basic hash table operations. So what's chaining? Chaining is a solution to handle the potential collision issues in storing data into a hash table. When chaining is used, the basic structure of a hash table will be an array, and each index in the array will be used to store a linked list. This idea helps address the collision issues. When it comes to inserting new data into a hash table, if two data points have the same index computed by the hash function, they will be added into the same linked list at that index, one element after another. So you will be able to chain them up at the same index. And that's why this method to handle collisions is called chaining. This structure introduces some challenges in searching for or deleting elements. For searching, when you are given a target key and compute its index, you will need to check possibly all the elements in the linked list at that index. The same can be said for the delete method. You will need to find the target element based on the given key first, which means that you need to check possibly all the elements in a linked list at a particular index. Let's go over an example to see how things work in a hash table when chaining is used to handle collisions. A single array like this would be good enough as the data storage for a hash table when chaining is used. We will name this array table, and it is initially empty but comes with a fixed size. The input data that you get to insert into this array is as follows. There are 4 key and value pairs in total. In each pair, the key and value are separated by a comma. For example, in the first pair of data, the key is cat, and the corresponding value is integer 5. To insert the input data into the hash table, you need to compute their positions by feeding the keys into the hash function. Based on the hash function, given a key, which is a string, you need to find the corresponding digits of each character in that key from the ASCII table. After that, you will need to add up the digits. In the end, you will divide the sum by the size of the hash table, which is 11. For example, the key of the first pair of data is cat, and when you feed the key into the hash function, it will compute its position accordingly, and the result is 5, which means it goes into the index of 5 in the hash table. When you do the same to the keys of the other pairs of data, you will end up with the following indexes. Based on the computed indexes, we will insert the data into their positions in the data storage. You may notice that 2 pairs have the same index. I mean the pair whose key is cat and the other whose key is ant. How do you insert them into the same index? With open addressing, that's not possible. So you have to find a different position for either of the 2 pairs of data. However, with chaining, you are able to insert 2 or more data pairs into the same index. The array named table is not being used to store integers. Instead, each element in the array is a linked list. Each data pair will be a node in one of those linked lists. Because of that, 2 pairs of data can go into the same index, and they will simply be 2 nodes, one connected to the other. Let's demonstrate that via an example. Starting with a pair whose key is a cat. It will be the first node of the linked list at index 5, like this. After that, you will insert the pair whose key is fox as the first node in the linked list at index 4, like this. After that, you will insert the pair whose key is dog as the first node of the linked list at index 7, like this. After that, you will insert the pair whose key is ant. It goes to index 5. Since there are already some other nodes in this linked list, you need to traverse all the nodes till you get to the end of that linked list, and insert a new node representing this pair of data, like this. So chaining is about using linked lists to chain up all the data pairs that are supposed to go into the same index. As such, no collisions would happen between such data pairs. Now you know how things work when chaining is used to handle collisions. Let's implement the basic operations of a hash table accordingly. We will start by preparing a hashtable class. Under this class, we will create a linked list named table whose size is m. Each node in the linked list aims at storing a key and a value pair. So the class representing a node will look like this. For simplicity, we are assuming that each node deals with paired data whose key is a string and the data is an integer. Beyond that, we also need a hash function that helps compute the index given a key value underneath the hashtable class. Now, we are ready to implement the basic operations of a hash table, including the insert, search, and delete methods. We will start with the insert method. The insert method takes two parameters. In combination, the two parameters represent a pair of data, because one represents the key and the other represents the value. The first thing the function does is to compute the index based on the given key. The index will be where the new pair of data be placed. After that, the function checks if there is already a linked list at the index in the data storage. If not, it will move to create a new one. After that, it will add the new pair of data as the last node to the linked list at the corresponding index. That's everything about the insert method. As you can see, the hero here is the linked list. It's responsible for chaining all the paired data as nodes that goes into the same index of the data storage. Let's look at the search method next. The search method takes a single parameter representing the key. Same as the insert method, the first thing the search method does is to compute the corresponding index based on the key. If there is a linked list at the corresponding index, the search function needs to check one node after another iteratively in the linked list. If the key is found somewhere, you will immediately end the iteration and return true. Otherwise, you will return false in the end. It's worth emphasizing that when you need to be sure that the given key can't be found in the data storage, you have to iterate through all the nodes in the linked list at the corresponding index. As you can imagine, if the length of the linked list to iterate over become long, the search could potentially take a long time. That's a search function. Now let's look at the last basic operation, the delete method. The delete method takes a single parameter representing the key. It will compute the corresponding index based on the key first, and searches for the node with the key afterward. It does the search in the same way as the search function, by iterating over all the nodes at the corresponding index. If a node with the key is found, it will delete the node in the linked list and return true. Otherwise, it will return false, as the key cannot be found in the data storage. That's everything about the basic operations of a hash table when chaining is used to handle collisions. Let's move on to discuss the time complexity of the basic operations. We will start with the insert method. What does the best case look like for the insert method? When you can insert the new pair of data as a node in a single step. That's when the new pair of data is inserted as the first node in a linked list. The time complexity of this case is big O of 1 because it takes constant number of steps to do so. What about the worst case? In the worst case, all existing data in the data storage are stored in the same linked list. Like what do you see here in this example? If there are n pairs of data in a hash table, all of them are chained in the same linked list, and the new pair of data will also go to the same linked list. then you have a worst case. That said, the time complexity of the worst case is big O of n, where n represents the number of pairs of data in the hash table, like this. Now, let's talk about the average case of the insert method. The key assumptions for the average case analysis is that the hash function distributes keys uniformly across all the indexes. We will assume that a hash table contains n nodes in total, and the size of the data storage is n. Then, same as what we covered on open addressing, the load factor alpha is calculated as n divided by m. The load factor measures how full the hash table is in general. To be specific, when chaining is used, the load factor alpha also represents the average node numbers per linked list, or say per index, because we assume that the hash function distributes keys uniformly. This is based on some intuitive understanding and often straightforward enough. If you want a formal mathematical deduction, you will need to pick a random variable representing whether an arbitrary number of key is hashed into a particular index, estimate its probability, and calculate the expected number of nodes per index given n nodes in total. We will skip this step here considering how intuitive the n divided by m is to represent the average number of nodes per index. That said, the time it takes to insert a node at the end of a linked list is all about traversing all the nodes in a linked list, which is in proportion to the number of nodes, which we already know is represented by the load factor alpha. Additionally, to account the constant number of steps it takes to actually insert this new node, we also need to add 1 to those steps, which gives you 1 plus alpha. So the average time complexity of the insert method is big O of 1 plus alpha. You may wonder if the 1 is necessary here. It is, because alpha could possibly be a number that's smaller than 1, and a number that's so small and it's close to 0. Because when the hash table is empty enough, there are barely any nodes at any of the specific indexes. That said, 1 is truly necessary here. As for the search method, the time complexity analysis is the same as the insert method. The major cost of the search method remains the same as the insert method, which is to iterate through the linked list at the corresponding index. I mean this block of code. As a result, the best, worst, and the average case analysis of the search method is the same as those of the insert method. The same thing can be said for the delete method. The time complexity analysis of the delete method is the same as the insert method. Now you understand what chaining is, how it is used to handle collisions, and the hash table implementations when chaining is used. That's everything about this video. Hope you learned something new.